hide that. So, it's recording the screen without your faces, and it doesn't capture any of your sound or anything like that. So all of that is off of the recording, like I say every week. Um, so trying to keep track of the 3 clocks. My laptop says it's 10:33. My phone says it's 10:31. Is anybody in the school building? What is it? A reasonable time there? I don't know. No comment. Okay. Excuse me. So we'll go through and take a little bit of a look at the crack the circuit. There were a few folks that um, enjoyed that, and there were a few folks that had that really struggled with that. So, and it was a pretty even mix of people that were commenting on, hey, that was pretty slick. I got 17 or 18 and or 16 or 17, and at that point they start asking some weird things. And then there were an even number of people that were like, dude, this doesn't make any sense at all. So we'll go through and just make a little bit of do a couple of examples on there to try to make sure we know what's going on, and we can see what happens there. And then we'll discuss some things with electric power, um, because the next assignment or part of the assignment today starts to deal with electric power, and that's where even if you're not going into physics, engineering, science, technology stuff, the electric power stuff is a really relatable thing as once we start getting used to calculating and making observations with that. So switching over to the crack the circuit thing, you can now see the crack the circuit website, I hope. Can I get a head nod? Thanks, I appreciate it. The one guy, guess who I'm looking at? The one guy with the screen on. I appreciate it, man. And if now you want to turn off your camera, I'm not offended. so I go new game, and I won't do all of these, but I'll do a few just to make sure that we're comfortable with what's going on, and we get what's happening here. So the circuit box, what's inside here, to unlock it, we need to draw a circuit that behaves like that light bulb does. So swipe to draw a line. So I'm just going to swipe there, erase. Whoops, cease. Whoop. Yep. I want this. There we go. Uh, Switching from way, I'm all over the place. So if I want to drag the battery in, I put the battery there. I want that to be a circuit there. There. And this part here is not being used at all. Um, so, but we just see, hey, drag the battery in and it kind of goes through and we have that connection. Um, This one, they say, hey, if we close the switch, the bulb lights up. So we want this switch to be able to control that light bulb. Um, and I don't know if this one, no. So we just want to build something where a switch turns the light bulb on and off. So if I say, hey, I'm going to put the battery there, I'm going to add a wire, and I'll throw the switch in there, drag the bulb down. So right now we have just one path. If positive, if we think of positive charges as being the things that are moving, then the battery is motivating all of the positive charges here to go this way, right? All positive charges would get pushed away from the positive side of the battery through the filament, through the switch back over. Once we turn that switch on, bulb lights up, turn the switch off, it should turn off. Then I think this is the one, yeah. So now this is the one where they say, hey, if you tap it, that's like unplugging it, right? Or unscrewing it, removing that bulb. And we see that in this one, if I remove this bulb, both bulbs go out. If I check the other bulb, if I remove that bulb, both bulbs go out. So this is just trying to get us to kind of see how these things get put together. So if I, again, put a battery in over here, wire, light bulb, light bulb, shoop, shoop. So the point that we're trying to ensure we have for this, the big emphasis on this is that if I remove this bulb or if I remove this bulb, both bulbs go out because there's no longer a path for current to flow back to the battery. right? If I remove a bulb and replace it with something, well, then yeah, maybe we could make it work. But we're just saying, hey, you remove the bulb. So if we take this bulb here and just unscrew it and remove it and don't make any additional connections, well, flow wouldn't be able to go through this spot because there's no path there. So that bulb simply wouldn't light because we removed it. And if this bulb is removed, no flow gets to this bulb. That bulb doesn't light either. And now with this one, if I remove this bulb, that bulb remains lit. I put that bulb back in. And if I test the same thing with this bulb, remove it, that bulb stays lit. So this is a circuit where the two bulbs function independently. So if I put the battery here and put this bulb here, that bulb works as it is. There you go. And now we need to find a way to get another bulb in here that functions independently of this one. So if this one's on or off, no matter what, we still want this one to be able to light up. Right now, as it is, this bulb is not lit. The one on the right in the diagram is not lit, and the one on the left still lights. So we know that that's working. And the simplest way to go is just to say, hey, I'm going to go like that. And now I have two bulbs that both work independently. It's really like having two different bulbs just separately connected to that battery, right? So that's a parallel circuit where both ends of this branch, if we think of this vertical line as a branch, the top end of this branch connects to the one side of the battery, the bottom end of this branch connects to the other side of the battery. That makes this independent of this. Whatever happens to the bulb on the right has no effect at all on the bulb on the left. And that is true when both edges of a branch connect directly to the battery, like electrically connect directly to the battery. So that's what we're looking at with those sorts of connections and those sorts of circuits. Oops. Turn the light on, they both go. If I remove that bulb, that one goes on, that one goes off. So we're just continuing to look at those sorts of things for circuits. And I think that that's far enough to kind of convey what's going on with that stuff. If you have any questions, I'll give you a couple of seconds. Do you have any questions on the crack the circuit stuff? You can either say something or chat something. Getting the head shake. All right. Giving you a couple of seconds. Sometimes it takes a little bit to figure out what question you might have. All right. It seems like we might be good there then. Then, oh, I should talk about this. I buggered things up this morning when I was setting things up. Or I guess last night when I was setting things up. I made an initial version of the building circuits assignment that I mistakenly gave everybody the same document that they could all edit, and then as opposed to giving everybody their own document. And the electric power form we'll take a look at in just a second. Somebody commented on the chat, and we'll take a look at that in just a second. I want to make sure that I address my mistake here, and then we'll get to it. Thanks for asking. So on my screen here, you should be able to see that, hey, there's one that's titled 0311 messed up version building circuits, and there's another version that's titled 0311 good version building circuits. There are only 8 people that see both of these, whoopsies, that see both the messed up and the good version. Those 8 people worked on the messed up version. They just got there before I had a chance to fix it. If you don't see the messed up version and you only see 0311 good version, then just do that one and you're good. If you see the 0311 messed up version, then you started working on that and you might have submitted that first before I had a chance to, before I realized that I messed that bugger up. So if you see the 0311 messed up version, I sent you a little emails asking you to like copy and paste your answers from that into the good version. Because if I have 8 people editing the same document, it's really tough to figure out who did what, and then to also assign points for the completion of that stuff. So my apologies for that. I posted in the stream sorry about that comment. So again, if you only 8 people, I think right now see the messed up version. So hopefully we can work through that part. All right, then electric power. Let's see, we'll go. So we've talked a bit about electric potential. And we've said that that is, oopsies, come on, energy per charge. And we've talked about current being charges per second. So when we're going through and looking at these things, here, we'll go, floop, floop. So when we're looking at those 2 main things, energy per charge and charges per second, it turns out that if we take that electric potential and we multiply by the current, then what we're doing is we're taking energy per charge and we're multiplying that by charge per second. Yeah. And so this is like looking at fractions. Here, I'll see if I can, I really like the fractions where there's just like the horizontal line as opposed to the that little slash. So I'll do it where we see it as an equation here, and we'll see if that, in my mind, that makes things a little bit cleaner. Super tiny, I'll change it in a second. So energy per charge times floop, floop, charge per second. And now I'll make it big. Right. And so if we're seeing it like that, we have energy over charge times charge over energy. And what we might notice, if we have charge on top over here and charge on bottom over there, in math class, we'd say you could do something. What can you do if you have charge on top of one side and charge on bottom of the other? You can cancel them out, right? So I don't know what you call it in math class. Some people, sometimes in math class, they'll say you can cancel them out. Sometimes they'll say you can reduce to 1 or they become 1 or something. Different math classes have different preferred languages there. So I'm just going to use the phrase cancel. If I have charge on top and charge on bottom, I can cancel them out. They become 1. And then I have energy on top and seconds on bottom, or seconds measure time. So that's maybe another way of saying, well, I'll leave it as seconds now since I put that earlier. We can also say that that's, get another fraction bar in there. That's energy over time, right? So this, if we take electric potential or voltage and multiply by current, that gives us electric power. That tells us how quickly we use energy. We use electrical energy. So I'm going to type that in as our equation, another equation here, just so we see the whole thing. So I'm going to say big P for power. Yeah, I'll just type out the word power. Equals and it's, no, that's not a fraction. It equals the potential difference, voltage, times current. And that is a variety of ways to say what this becomes, right? So power is, we can say it's how quickly energy is used. It's energy over time, right? So we can say that it's how quickly energy is used. Some folks will say, instead of how quickly energy is used, math departments really like the word rate. So some people might say the rate of energy used. They might say rate of energy transfer, or how quickly energy is transferred. So those are all just kind of different ways of saying the same thing. Power is how quickly energy is used, or how much energy is used per second. If you're using a lot of power, or if you're generating a lot of power, you're doing a lot of work, you're transferring a lot of energy very quickly. Um, uh, you can have a large amount of power and a short amount of power, or a small amount of power, that both do the same amount of, or both transfer the same amount of energy, just how quickly that happens, right? So I've got my little box for my earbuds, and if I'm holding it right here, and I lift it up to there, well, if we go back to first semester stuff, right, it has one bit of gravitational energy here, it now has more gravitational energy there. I've done work. I've given energy to the little earbud case Earth system. I've increased the energy of that. Now I can do that really slowly, moving it up little by little by little by little to that spot. Or I can do it more quickly, going, whoop. I've used the same amount of energy because it started here, ended there. I've given it the same gravitational energy in each case from here to here. But if I do it in a very short amount of time, looking at this relationship, if I do it in a very short amount of time, then the number on the bottom is smaller, and so the power is larger. So if I go very quickly, whoop, that's much more power than if I go. Right? So if I take all that time to do that same amount of energy transfer, then the energy part is the same, but the time part is much larger. So the power is less. Well, the the same that how to say this. So really just trying to convey that power isn't just how much energy you use, but how quickly you use or transfer that energy. And then if we look at ways to calculate it, we now have kind of two versions already. I'm just going to bring those down here. One way to calculate it is that. Another way to calculate it, oops, pardon me, I'll just try it for consistency's sake. I'm going to try to use this equation editor thing. We can also say in general terms that power is energy transfer over time. So we can do that. And then if we look at that first relationship with electric current, being the potential difference times current, if we look at the electricity version, we can also do a bunch of different substitutions in here as well. So if we go back to some other things, here, I'm going to just take this equation and slide it up. Oh, it won't let me enter. I need to undo, enter. Nope, come on, enter. Good Lord. Okay, so now if we're looking at this relationship with power, remember we did Ohm's law stuff. a while back where we said current through an item equals, and that's where we would put in the potential difference over the resistance. So we can go through and do some substituting, and then down here, if instead of I can, oh, for Christ's sakes, if instead of saying potential difference times current, I can say it equals this potential difference V, and instead of times R, I can plug in this stuff times another delta V over R, right? And if that's the case, then this really becomes, come on, get in there. This really then becomes a more compound, or more just really a fraction, right? I can say delta V squared over R. So that's one way to look to another way to calculate electrical power. If we do another substitution and instead we substitute and solve a plug in for delta V, then another way to calculate power is to say power is, and then it becomes, another way is to say I squared times R. And that's a really common way for electricians and electrical engineers, excuse me, for engineering folks to talk about it. They'll talk about I squared R losses. They'll just use that phrase because if you have an extension cord or some wire that is designed to carry a certain amount of current, but it starts to get hot. Well, if it starts to get hot, then that means that there's maybe a little bit more resistance in there. And you can talk about the heat that radiates out of it as being an I squared R loss. But these things are all ways to calculate power. Um, so those equations and these concepts are all included in the video in the Google form on power. So when we're looking at classwork, when we're looking at this electric power assignment, that's all in there. There's a video. There's my dog. There's a video on the second page that it's like 4 minutes or so, I think, that goes through and discusses all of the electric power calculations and goes through kind of quickly how things work and what things are. And there are some sample calculations done in here. These questions that I ask in here are really all just trying to make sure that what they did in the video makes sense and that that you can follow along. So that's a lot of me talking. I'll give you guys some questions now. Some people have had some concerns. I got an email or two, and there's a comment on this on the form, and some questions or concerns on the form. So if you have specific questions on the form, let me know, and we can take a look. So right now, just to clarify, sorry, um, I'm pretty much done. So if you have questions on the form, you can ask. We'll go through and discuss. If you feel like you're done too, hey, you can hang up. I'll catch you on the flip side. What you got? Have a good one, man. Thank you, folks. We'll see you. Bye. Have a good one. We'll see you.